Hello everyone, welcome to MPLS and Segment Routing Basic to Advanced Learning series. This is our second session, and these will be some series of sessions where we will talk about some aspect of MPLS and then move to segment routing. So today what we will be talking about is first, why MPLS? Some more reasons basically. In our first session, which is already available on YouTube, I have talked about this part, why MPLS, and given some reasons. Then today I will cover some more reasons behind that. After that, we will be talking about LDP, and that is again why we needed LDP. One of the fundamental aspect for packet forwarding in MPLS is that the packet has to be labeled. So we need a protocol which can give the label or basically supply the labels. But does LDP was the only option or were there some other considerations? That is what we will talk about in this second bullet. Why LDP or were there any other options? And then I will talk about some of the working experience with LDP, and then we will close this second session. So with that, my name is Sunil Pareek, and this video is a part of our live course which is MPLS to segment routing. In case you want to know more, check the description for this video. So with that, let's just jump into the discussions. So unified network infrastructure. If I may ask you, the reason why IP got so much popularity. If we go back in the past, there were a couple of other protocols like Apple Talk was there, IPX was there, but then it was IP which won the race. Today, every network uses IP. What's the reason behind it? One of the possible reason is that IP provided a mechanism on which you can carry anything. What I mean by that, IP started with data transport. We can transfer the data packet from one point to other. Then telephony came on it. Your VoIP phone, voice over IP, right? Then soon we started video also. So this was the single transport which enabled all these newer demands. And that was one of the reasons it survived for the longer term. Same way, if I take a step back, let's say this is at OSI layer 3. At layer 2, we have Ethernet, which is a robust protocol. But the problem with Ethernet or layer 2 Ethernet based network is you cannot scale them. Beyond a certain size, a L2 domain start causing some issues. But then at the same time, there are certain applications which need layer 2 connectivity. If you talk to application architects, they will say that from point A to point B, I need a layer 2 path, despite the limitation of Ethernet in terms of reliability or scalability. Or in fact, one of the famous application is VMware vMotion, let's say, that need layer 2. So network engineers, when they were designing the network, they can't avoid a layer 2 network and layer 3. So when MPLS was invented, as I said in my previous session also, there was no protocol field. So MPLS actually enable the transport of layer 2 as well as layer 3 on a single unified infrastructure. All you need is just enable MPLS in the network. You carry your layer 2, not only Ethernet, HDLC, PPP, if you recall what are those, not that widely known today, but in the past they were there, and then your IP. Both can be transported over MPLS. Both were widely adopted in their respective domain. For layer 3 IP, for layer 2 Ethernet. But MPLS had gone one level up and provided a unified network infrastructure for both of them. By looking at a MPLS packet, you cannot tell whether it is carrying an Ethernet frame or it is carrying an IP packet. That is the advantage. MPLS uses this common infrastructure to forward all type of packets. Service providers, they only need one unified network infrastructure to carry any customer traffic. Customer want layer 2, answer is MPLS. Customer want layer 3 connectivity, answer is MPLS. So this is our first reason for this session. Now let's move on to the second one. The second one is BGP free core. What I mean by that? Let's just look at these four set of routers. Here I have certain subnets, let's say 10.1.1.0, 2.1.0, 3.1.0, and list just goes on. If there is a endpoint here which want to reach these IP addresses, now as we all know that IP is a destination based forwarding. That means I need these route on these devices also to forward the packet. Now this is not a problem because I may have some handful of route. What about you have full BGP internet feed? That means all of these nodes in between need to have all the routes with them so that this guy can forward the traffic. But basically, from a high level, what we are looking here, if my PE1 forward the traffic somehow to PE4, then PE4 will have all these routes anyways. All these BGP routes PE4 have, then PE4 can send it forward. So these intermediate node, what they are doing, they are just forwarding the packets to PE4. But still, because IP is a destination based forwarding, these P1 and P2, they need full routing table. But with MPLS, that is not the case. If I enable MPLS on this path, this entire path, if MPLS is enabled, I don't need any route, any of these routes on these devices. They are not needed. P1 and P2, they will forward the packet based on labels only. So what the slide says here, that if the packet are sent to destination that are external to the service provider, as let's say BGP feed, these IP prefixes must be present in the routing table of each router. This is not the case with MPLS anymore because MPLS forward the packet based on labels. Incoming label will be swapped with a outgoing label. That's it. That's the another advantage of MPLS. Let me give you a few more reasons. MPLS One of the very famous application of MPLS is L3 VPN. And MPLS made VPN provisioning so easy that I can challenge to find even a single service provider which is not running L3 VPN. In this video, we will not talk much about it, but this provisioning was made very much easy with the concept of VRF that I will talk in some of our upcoming sessions, that it was very easy for the service providers to provide VPN services layer 3 or layer 2 to their customers. The next reason for why MPLS is traffic engineering. We have talked about this briefly in our session 1 also, but let's say, as I was saying, that IP is a destination based forwarding. So let's just take a network like this, where I have upper path which is less in the hop counts, and then there is a lower path which have more hops basically, but bandwidth wise they both are same. But my IGP will always prefer this dotted path. And if I have some devices here, let's say R1 and R2, if any traffic is coming from R1 or R2, from R3, it will always follow this upper path. And if I try to play with some metrics here, then it can go via lower path. But again, it is a destination based forwarding. So here R1 or R2 cannot take the decision whether they want to go via the upper path or the lower path. It is the R3 which will decide. But with MPLS, I can make a LSP, label switched path, like this, where traffic from R2 I can send via lower path, traffic from R1 I can send via upper path. This is a feature for traffic engineering, and that is why traffic engineering enable us to use the network resources in a much more optimal way. And in case of failure, let's say if this path fail, let's say this link fail, this LSP, the lower LSP, will be immediately rerouted via this upper path. So this is the another benefit for MPLS. Right? So I have given you enough reasons why MPLS got so popular. Now let's just look at some of the protocols which actually supply the labels. Because as I told you, MPLS forwarding cannot happen without labels. Like IP, it packet forward based on the prefixes. In MPLS, packet forwarding happen based on labels. So we need something which can supply the labels. And that is actually label distribution protocol. So by this explanation, you may be convinced that we need label distribution protocol to distribute the labels, because that is how MPLS forward the packets. But when I have IGP help me to find a shortest path in the network. Can't those IGP help me to allocate a label as well? Right. So let's just look at this aspect, that why we needed LDP. So Here, if we look at the label distribution methods, very well there can be a certain way where IGP, they not only supply the shortest path via the network, they also supply the labels. So why in the first place we came up with LDP? So back in the history, this was the question that was there on the table, that for MPLS we need labels, but who will supply the labels? And at first, these industry people looked at these IGPs only. And I am assuming that you guys have certain knowledge about these IGP, but they are categorized in two categories. One is distance vector. The second one is link state. If I want to highly simplify this, distance vector is something like, let's say you are living in a city. So you know your neighbor know their neighbor, and their neighbor know their neighbor. So if you want to reach somebody in your lane which is at a distance, you just connect with your neighbor. He tells that, okay, I know this guy, that guy tells you about that, the next person, and that is how the information propagate and reach to you, that yes, the person X sits in the same lane 4 or 5 houses down to yours. So you are basically relying on your neighbor. Link state is something like, let's say you are living in a village where everybody knows everybody else in that village. You can go into any house and ask the information about anyone who is living in that village. There are very high chances that they know each other and they know very well, right? So this is at a high level with this very simple analogy, distance vector versus link state. Now coming back to our label distribution. So with this distance vector, it was quite easy to modify and include the labels, because when my peer is advertising me a route, he can also allocate a label and send it across. But for the link state, they don't advertise routes, they distribute database. And then the routes are derived from those LSAs. Example of your link state is OSPF or ISIS. So definitely this was not that easy with the link state routing protocol to supply something else as well, like labels in our case, along with this database. And this database has to be identical on all the nodes in that area, right? If you take OSPF as an example. So it was not that straightforward. And then there were multiple of these protocols. So these industry people thought that if they need to use IGP, they need to modify all the protocols. Rather than let's just invent something new, which is LDP, and make LDP work with all these protocols. Your routing protocol provide the destination and the shortest path. LDP supply the label. Simple logic. So out of the two choices that were available, piggyback the labels on an existing IP routing protocol versus having a separate protocol to distribute labels, industry went with this option because this was easy rather than modifying all the routing protocols. So a new protocol from the ground up, independent of the deployed IGP, was invented, and that was LDP, and it can work with any IGP. So whatever IGP you are running in your network, LDP can allocate the labels. Now you may be wondering that here I am saying only IGP. What about BGP? Who will assign the label for the BGP prefixes? Let's say there are 10 routes in BGP table. So for that, BGP only was modified. It was easy to modify BGP. So LDP assigned label to only IGP destination. BGP assigned label to only BGP based prefixes. I hope this is clear. And now let's just get into some of the LDP know-hows. So LDP, like any other IGP, right, it first has to discover the neighbor. Let's say R1 and R2 neighbors, they need to discover each other. And how they discover? Basically the way your OSPF discovers the neighbor or your EIGRP discovers the neighbor. They send hello messages. Once they discover each other, then there is a session establishment that happens. This is actually a TCP session. This discovery happens via UDP. And once this session is there, LDP session between R1 and R2, then on top of this, your label advertisement happens. So R1 will allocate, let's say there are 10 prefixes known via IGP on R1. Our LDP will allocate a label to each of these prefixes and send to R2. R2 will do the same thing. From the configuration perspective, if I just show you a snippet from my lab, all you need to do is on a Cisco device, this is iOS XE configuration, you enable MPLS label protocol LDP, and then on the interfaces which are connected to other peers, you configure this command. Configuration of LDP is very easy. You just need these command and LDP will start functioning. Your neighborship will come up. If I show you certain show commands, let's say here this show MPLS LDP discovery detail. First you see this LDP identifier, which is your router ID, LDP router ID. Now you may be asking what this :0 means. So basically there are two ways by which labels can be assigned. One is per platform, another one is per interface. Per platform you will see this value 0, and these days labels are assigned per platform only. Per interface I had only seen with ATM. And don't worry if you haven't heard this name. I'm not talking about the ATM from which you withdraw money. No. This was something that was used in the past in networking. Nobody is using these days anymore. So forget about per interface labels. Per platform works just fine. Then on the Ethernet, this is the underlying interface. Transmit and receive, which is a good signal here, and then this is my hold time, hello time, hold time, all these things, right? And then if I do show MPLS LDP neighbor or LDP sessions, I can basically see the neighborship. If I execute this command show MPLS interfaces, I can see that there are these interfaces which are enabled with LDP. So you need to enable LDP, then LDP will come up. I will not go in much detail for this. If you are trying this in your lab, feel free to use that config snippet. The configuration is very easy, or put it in the comment box. I can give you the complete config also, and then it should just work. However, in my working experience with LDP, I had seen certain issues. So let's just talk about those. So one of the issue is, as I was saying, this is R1, this is R2, and I want to have a LDP session between them. And if I am having some loopback here, which are my router IDs, LDP router IDs, then they should be reachable to each other. If they are not, your LDP session will not come up. You can verify that with this command, show MPLS LDP discovery. If you see this no route, that means 10.254.254.2, I cannot reach to .5. Those routes need to be there. Then only LDP session will come up. The second issue is LDP work hand in hand with IGP. Your IGP supply the path. Your IGP decide which path to go. LDP only gives the label. So there may be certain chances where IGP says that go via, let's say there are two paths available, 1 and 2, go via path 1. But LDP is still converging. It had not assigned the label for this path. That means your traffic will get dropped even though there was a second path via which you had the label also available. Just because your IGP said go via path 1 and LDP is in the process of allocating a label, you will see some traffic loss. And for that LDP IGP synchronization, there is a feature that was developed. So the point that I'm trying to highlight here is, and we will not drag it much, that these two protocols work hand in hand. If they are not synchronized with each other, there will be issues. If you need more details on this, just let me know in the comment box. Then the session establishment. As I was saying, the two LSRs, they discover each other by LDP halos, and then they make a TCP connection on this port. And once this TCP session is established, this LDP session is established, the label advertisement happens. UDP halos are only to discover. TCP session is needed for label advertisement. And one of the common interview questions that we get is, like, let's say I have these two devices R1, R2, and there are two links between them. How many LDP sessions I will have? Remember, LDP session is a TCP session between these loopbacks. So you will have only one session, even though your discovery via hello will happen on both the paths. Right? So you will have only one LDP session. And the job of LDP that I had told you so far is to allocate the labels. Right? So let's say I have this R1, I have this R2, and here I have certain loopback, let's say 1, loopback 2, loopback 3. 3 loopbacks I am configuring. with IP address, let's say 10.1.1.1, 2.1.1.1, and then 3.1.1. 3 loopbacks. I am advertising those via IGP. That means they are IGP routes. So R2 will assign a label to these and send towards R1. R1, what it will do? R1, because it is getting, let's say we are running OSPF here. LDP is also. So R1 will receive all these 3 routes via OSPF. And what I said, LDP assign label to all the IGP destination. That means R1 will also assign a label, let's say label 50, 51 and 52 to these 3 destinations, 1.1.1, 2.1.1 and 3.1.1, right? So label 50, 51, 52 are assigned by R1. R1 will advertise these labels to its peer, including R2 also. So R1 will send these labels to R2 as well, that these are 3 IGP destination. I had assigned the label. LDP does not care that R2 is the originator. R2 only advertised these routes to me. But those routes are advertised by OSPF, not by LDP. LDP's job is only to allocate labels. There is no concept of split horizon in LDP. So then, how does basically LDP works? Right? Because this is clearly a problem. It may cause a loop also. Remember what I said. LDP heavily rely on IGP. So R1, even though it is doing allocation to the labels, it is distributing. But in the forwarding, it will only install the path which is given by OSPF. For example, let's say if we have this label forwarding information base, right? Show MPLS IP binding, which is your lib table basically, label information base. For this prefix, I have 3 paths, 3 labels I got from my peers, 22, implicit null and 26. Which one I will use? That will be told by the IGP. So in this case, we'll forward the traffic on this path only. So it is the IGP which is controlling this behavior. And that's why LDP never created such issues. For the path, IGP is the final authority. So with that, let's just conclude this module here. I hope this was informative and you have learned something new. I will see you in our next session. Thank you.